Okay, I think it's recording. Yep. All right, folks. Well, happy Monday again. So we were talking about momentum methods, right? We said, well, we talked about energy methods, and then kind of derivative of energy method or kind of related to energy methods are momentum methods. Now, the story is that now we are looking into the relationship between basically the time integral of forces that are applied to our system or object or particle and change in object's momentum. Now, we talked about principle of linear impulse and momentum, right? We derived that from Newton's second law. Went over a couple of examples on how can we actually use this to study the motion of an object. Remember, this is dynamics. The big picture is we are learning different methods that we can use to study the motion of an object, right? We are, generally speaking, in engineering mechanics, we're studying the conditions of objects, right? Now, in statics, we were studying those objects when they were in a static equilibrium or in equilibrium. General in dynamics, we're studying the objects when they are in motion, right? Specifically speaking, with some changing acceleration, changing velocity, meaning they have some kind of acceleration. Now, so we talked about linear impulse and momentum. Now I want to talk about principle of angular impulse and momentum. So what is that? Well, remember, I'm just giving you more and more tools to be able to study moving objects. That's the whole story. Now, when we're talking about linear impulse and momentum, we said, well, the whole idea is that now we get this integral of forces with respect to time and the relationship of that one with change in linear momentum, right? Linear momentum being mv. Now, in angular momentum, we still kind of do the same thing. It's the integral of forces, the time integral of forces and change in velocity. What happens is that in angular momentum, impact and momentum, position comes into play again. So now you have both time and position. Right? Remember, when we're talking about energy methods, we said, well, we don't care about the positive, negative, or direction of the velocity. And the whole idea was looking into force and its relationship with position, right, for an object. Linear impulse and momentum was mainly focused on force, time, and velocity, right? Not force, position, and velocity. Now, angular impulse and momentum brings that position into play again. So things get a little, I don't want to say messy, but you have more variables there, not only time, but also position, as well as velocity that you had from before. So let's write it. Did I use? Yeah. I probably should use this. Okay, so let's write it as principle of angular. Probably I can write better. Of angular impulse and moment. All right, so we start from Newton's second law. Same story, right? There's one thing that we are sure and we know we can use is Newton's second law. Same way we did, or similar approach that we did for principle of linear impulse and momentum. We start with Newton's law, Newton's second law, and from there we derive the relationship for this principle. Right? So summation of forces is equal to ma. Right? Now you can write this as, let's write it this way. In this case, do a cross product or of position on both sides. So say R cross summation of F is equal to R cross M. And I'm going to write A as dv dt. Right? Change of velocity with respect to time. Now, I'm going to give you what the final relationship is, and then I'll tell you how we got there and what is at least the general approach, the math behind it, right? So from this, you can actually get to this equation, and I'll briefly show you how it happens. So it's going to be R cross F dt is equal to HO 2 minus HO1. Now this is the final result. Now, how did we go from the one at the top to this one, to this relationship? Well, here is the trick, right? I can write this first relationship here as, think about it as R cross F dt is equal to R cross, or let me just write it here. Let's just focus on the right side, right? Let's write this as R cross M V. I want to show that this ddt is equal to what we have on the right side, right? This is just a side note to show where this whole thing came from. Where did that come from? If I take derivative with respect to time from R cross MV, this becomes dr dt cross MV, right, plus R cross M dv dt. Now dr dt is v, right? Velocity. Now we don't have, there is no argument there. Now velocity vector cross M velocity vector. M is just the constant mass, right? The quantity. So we take that out. V cross V, the cross product of two vectors, similar vectors, right? What is the cross product definition? Cross product A cross B, we have A cross B is AB sine the angle between them, right? If this is A, this is B, this is theta. Now, if we have two vectors, cross product of two similar vectors, same vector, V cross V, well, they are exactly on top of each other. So the angle between them is 0. Sine 0 is 0. So this whole thing becomes 0. So dt, ddt, this one, right here, R cross MV is equal to R cross MdV dt. So I can replace this right here with d dt R cross MV. If I do that, you take dt to the other side, left side becomes R cross F dt, or summation of forces dt, and the right side becomes a dr cross mv, right? Now, if you do that, again, I'm just giving you side notes, where did that come from? If you do that, this is what you get. You get R cross summation of forces dt is equal to d R cross mv. Take integral from the left side, right side. We define this as HO, as angular momentum. So this becomes what we got, the equation. The only thing you have to add here with HO defined as angular momentum, we define it R cross MV. So what this relationship is also important. This is the definition of angular momentum. Okay. Angular momentum. So we had linear momentum before, mv, right? Now we have angular momentum, r cross mv. So the relationship that I boxed at the top is principle of angular impulse and momentum. What does that tell us? It tells us the angular impulse on the left side applied to an object during an interval of time, dt, is equal to the change in the object's angular momentum. That's pretty much principle of angular impulse and momentum, right? So let me write it here. The angular impulse what is on the left side, this is angular impulse. Angular impulse. Right? Applied to an object during an interval of time is equal to the change in, let's write it this way, in objects angular moment. Angular moment. Right. The right side is basically change in angular momentum from point 1 to point 2. Right. So this is principle of angular impulse and momentum. That's pretty much it. Right. Kind of similar to principle of linear impulse and momentum. You see the integral form. What is added is just an r cross. So now you see the position also comes into play, right? Before we only had force and time and velocity. Now we have force, time, position, and velocity. Pretty much everything is just all together. Now, since this is a cross product, right? We're dealing with a cross product here. Now we get into the whole story of vectors, right? If you actually want to write this more accurately, this r is a vector, v is a vector, so angular momentum is a vector. So this r is a vector, force is a vector. These are all vectors, right? I just didn't put them there. Maybe I should have. All right, summation of forces is equal to mv. V is a vector. Right? So since this is a cross product, now the direction becomes not tricky, but I guess I want to spend a few moments on the direction. Right? Direction for angular momentum. Now, mv was pretty clear. Linear momentum, wherever the direction of v is, m is just a constant mass applied to it. So mv has had the same direction as v. But r cross mv, right? There's a cross product there, and r the position comes into play, position vector. So this you have to follow right-hand rule. Right? R cross mv, you just four fingers cross align the you can put it align the first vector r, pointing to where your whatever object you're studying is, and then v would be let me bring the picture here. Actually, I specifically put this aside to make sure that the points gets crossed. 1689. There you go. That is better than whatever I tried to explain. So this is the direction of h, angular momentum. Right? If you have your r and you have your v, so your the four fingers align with the direction of r. The palm of your hand, or better to say your four fingers, wherever, in any way you are more comfortable with right-hand rule. There are different ways of phrasing this. Four fingers bent in the direction of v, right? So v is, in this case, let's say upward, so in this direction. Your thumb shows the direction of angular momentum h. And that's how you can figure out the direction. So we are in kind of three-dimensional space, right? Not kind of, definitely. Before MV, because everything was in a plane, we could just get away with it without dealing with this whole right-hand rule. But now that we are dealing with a cross product, right, we have to be a little more mindful about the direction of angular momentum. So just as a note, direction for angular moment. H. As long as you know R, you know V, right? M is just a constant. So this could be, instead of V, this could be MV, right? This is basically just MV. M is just a constant multiplied by V. It doesn't really change the direction of V. That's why it's not there. This is R cross M. So this is it. This is the principle of angular impulse and momentum. Now, of course, there are some commentaries on that, right? What fun would it be? It wouldn't be fun if there was no commentary and other stuff attached to the whole story. Now, first of all, this gives you a lot of power. You have a relationship between position, time, force, and velocity, right? As opposed to before, as what you had for principle of linear impulse and momentum, which the relationship was only between force, time, and velocity. Right? Now, there is a special case that we deal with a lot when we are using principle of angular impulse and momentum, and that's when we have a force, as they call it, a central force motion, meaning that the force acting on the object, right, it stays towards the point. Think about the coordinate frame, and you have an object moving, like around. Now, central force is a kind of force that during the motion of this object, no matter where it goes, this force always stays towards the point that is fixed to a frame, to the frame. So if this is the frame, this is the origin, let's say this point is moving around. Let's say this point goes from here to here. Okay. Your force, the central force, as they call it, central force motion, in this motion, your force stays towards a fixed point, right? A point that is fixed in your reference frame. That's central force motion. Now, what is special about it? The special thing is that in that case, R and MV are aligned, right? If you have a frame like this, and this point is moving around, if this F always stays or remains towards this origin or this fixed point on your frame, F, like this R and F are aligned. Let me put it, I don't know. And then R cross F becomes 0. That's the whole story. So let me write it this way. If we have central force motion, as the way your book refers to it. Central force motion, right? I'll explain central force motion on the side. R is parallel or is parallel to force vector. R being a vector, force being a vector. So R cross F becomes 0. Now, let me define central force motion here, and then I'll show you what happens there. So central force motion. Write it this way. When the force acting on an object remains toward a point that is fixed, relative to a reference frame. That's the story of the central force motion. Let's keep it here. Now, here is what I'm trying to say. If I have a frame like this, let's say, let's draw it in general form. Axes right there. I have an object I'm tracking. I think I'm studying its motion. If this is R, where the object is, I can draw a better R, more straight at least. This is R. Now, in a central force motion, basically the summation of all forces, what you get as a resultant force, right, is going to be always pointing to some fixed point. Right? In this case, let's put it origin here. So this would be your force. Summation of forces. The resultant force. Are force in different directions, but the resultant force would be always, doesn't matter where you go, right? It always stays towards a fixed point on your reference frame. This is central force motion. Now, what happens is that R and F always stays parallel, or better to say aligned or collinear, but parallel is a better, more general term. So left side of this equation, right, integral R cross F, we said R cross product is basically first vector, second vector multiplied by sine theta. Now, if they are aligned or parallel, the angle between them is 180 degrees. Right? Sine 180 degrees is 0. So the left side is gone. You get rid of the integral part. So what happens is, what you get is H O at point 2 is equal to H O at point 1. This is that. Right? Basically, you don't have to deal with that integral form anymore. Now, when does this happen? Well, I'll go over a couple of examples, but when we are the most common coordinate system that we deal with this, you probably have guessed it, some of you, that it's polar coordinate frame. Just think about polar coordinate frame, right? This is polar coordinate frame. Think about this as X. Think about this as Y. And then you have your object there. This is your, let's say, R. In polar coordinate frame, you have your coordinates. Let me put it here. And let's say the motion is in this direction, so I can get a sense of E theta. This is your ER. This is your E theta. Now, the case that you are using polar coordinate frame is probably the most common situation that you have this central force motion, right? Because in that case, if your forces are only in R direction, then whatever is in theta and whatever is in theta is 0, then you're lucky. You're in this position that you can say, well, this is central force motion, so the integral part I can get rid of because resultant force is always in parallel to R. Right? Remember, this is R in Maybe you have to be, there you go. Let's see what happens in, without me adding more into this, see what happens in polar coordinate frame. If we look at the object, right? We are looking at the motion, central force motion, and we're looking at it in a polar coordinate frame. Look at the object in polar coordinate frame, polar coordinate system, maybe. And remember what we had there. We had R as a vector was R ER. We had velocity as VR ER plus V theta E theta. Right, so these were our velocity vectors. This was VR. This was V theta. And hopefully you remember VR was R dot and V theta was R theta dot or R omega. Now, if you look at it in polar coordinate frames, right, we get HO as being R angular momentum is equal to R. Right, we said R cross MV. That was the general story. So R is R ER cross M. Just keep M outside. VR ER plus V theta E theta. And we do a cross product. Right? Sorry. So R cross ER. Let me just expand that. So HO becomes R ER cross M VR ER plus R ER cross M V theta E theta. Now R cross ER, RER cross MVR ER, well, these two vectors are the same, cross product of two vectors aligned. We just talked about that. The angle between them is 0, so this is 0. This whole thing becomes 0. The second term, ER cross E theta. Now, remember the cross product, we are in right-hand orthogonal coordinate system. The general rule, if you remember, it was ER, E theta, EZ. EZ being out of the screen. EZ is always there, we don't really talk about them. We have ER, E theta, going from ER to E theta shows the direction of EZ. So in this case, EZ is out of the screen. EZ coming out of the screen. Now E cross ER, ER cross E theta will follow the arrow. E cross E theta would be EZ. Right? So that will give you HO, or angular momentum in polar coordinate system, becomes R, let me write it this way, R M V theta EZ. And this is aligned with what we said about the direction of angular momentum, right? Right-hand rule, going from ER to E theta, your thumb shows the direction of angular momentum coming out of the screen. This is what we were talking about here. So what we got here is aligned with that, right? If you're in a plane X, Y plane, or E or E theta, what is coming out of the screen would be your EZ, and that's your Z direction, right? This is your Z direction even in your frame there, your Cartesian coordinates. So this is what we're trying to get to, this. Now, what does this mean? It means that if we have a central force motion, again, R is parallel to resultant force, that means, I'll put it this way, so R V theta stays constant. Or put it this way, or let me just not put it here. So let me do it more methodological. This is the relationship here. So from there, you get R, R1, M1, V theta 1, EZ is equal to R2, M2, V theta 2, EZ. Well, you can get rid of, well, not M1 and M2. M stays the same in your systems, right? You're not talking about mass changing systems here. So kind of can get rid of these two. EZ and EZ, they're pretty much in the same plane, that means. So what you get is R1 V theta 1 is equal to R2 V theta 2. Now, after all this moving around, I just wanted to see where did this come from. So here is the story. Let me start from the beginning. We're talking about principle of angular impulse and momentum. Right? Left side is the integral form. Now we have both time and position in play. Right side is change in angular momentum. So pretty much the principle says change in angular momentum is equal to the angular impulse applied to an object during an interval of time. Now, this is the general story. Angular momentum R cross mv. Right? Wherever the object is, cross mv, velocity of the object. Now, we said the exception or special case to this general rule would be central force motion, which is a kind of motion that the force acting on, or resultant force, there to say, acting on the object remains towards a fixed point on your frame. You can think about that fixed point as the origin of your frame. It's the best way to think about it. That means R and resultant force are parallel, which means the left side of the equation, the integral R cross F becomes 0. Right? It's a cross product of two parallel vectors is 0. Now, we said, well, this is an interesting case, which means the angular momentum stays constant. Right? No matter where you are, as long as this is a central force motion, point 1 and point 2 during the motion, any point you want to choose, the angular momentum is constant. So whatever it is, R cross M1 at point 1 should be equal to R cross MV2. Right? R cross MV1 should be equal to R1 cross MV1 should be equal to R2 cross MV2. Position velocity 1, position velocity 2. Doesn't matter how it changes, as long as the motion is central force motion, they should be equal. Now, we said if you look at this in polar coordinate, using polar coordinate, or study this central force motion using polar coordinate, what we get is that R1 V theta 1, or probably I should have put cross to be more more accurate, but R1 V theta 1 is equal to R2 V theta 2. Now, where are V point 1 and point 2? Well, point 1 and point 2 could be any point during motion, as long as we are in central force motion, remember. If we are not in central force motion, defined here, then this does not apply. We have to go back to the integral form of the equation. All right. So that's the general story. Now, a few things are new now we have position, so it's different from just time that we're dealing with when we're looking into linear impulse and momentum. We are using, for most cases, when we have central force motion, we just use polar coordinates, and we care about what happens in theta direction or direction as long as we're in central force motion. All right, so that's the general story. Now, of course, this becomes a little more complicated compared to linear impulse and momentum and energy method. Right? So we're building our way to this. We are building our way to this, and at the same time, more powerful. You have some more variables you can use to study objects and their motions. All right. Let's look at an example. I'll see if it gets better. Any question up to here? The theory of the story and where did that come from, and everything started from Newton's second law. Nothing. This is some mathematical procedure and some special case central force motion in that, but the whole story started from Newton's second law. Right? We said R cross on both sides, from both sides, or multiply both sides by R, the cross product, and then did some hand waving and a little bit of math manipulation, but to get into principal angular impulse and moment. All right. So that's the equation. Angular momentum. Remember central force motion. In that motion, we get rid of the integral part of the left side, so we only care about the right side, which means angular momentum stays constant during the motion if you have central force motion. And you study that in polar coordinates. The best way of studying. Now let's see how does this help us solving problems. All right, let's start with this example. I actually put aside these figures from the book because I realized if I don't draw them, you will never understand what I'm trying to draw. This one is actually not that bad. I could probably draw this one. So we have this mass, sliding mass can slide easily on this bar. The bar is rotating around this pin. Right? Why not? It's dynamics. Make things as complicated as possible. So this is a pin there. This bar is rotating around this pin. This whole thing is in horizontal plane. So think about it this way, not this way, this way. No gravity in this direction. So it's rotating. Right? This is the bar. This slider can go back and forth on the bar. There's a spring at the end. Spring is fixed. I mean, it can't go further than here. Right? It's attached to this end. There is no friction between the slider and this rotating bar. Now, when this bar starts rotating, remember previously from kinematics, we kind of talked about this and we looked into this even when we were looking at dynamics of an object, a particle. We said, well, when this starts rotating, right, this bar starts moving away from the center. An example could be any, I gave you few physical, I guess, experiments, or not physical experiment, an experiment or a thought experiment. You can think about that. If you attach some heavy object to the end of a rope and it starts turning around, start rotating and holding the rope and turning and rotating around, right? And start rotating that around, you will see that obviously the rope is going to be under tension. Well, because the object starts moving away or tries to move away from the center or axis of rotation. It's the same story here. Right? The slider is trying to move in this direction. And once this rotates, this bar is rotating. So the problem statement, let me write it this way, says the bar rotates in horizontal plane. That's important. So the bar rotates in horizontal horizontal plane. Let's write it this way. About, let me be more accurate. About is smooth, about we want to get rid of all the possible frictions, about a smooth pin. So no friction between the pin and the ball. Pin at the origin. We don't need that. 40. We have 2 kilogram. They refer to it as a sleeve here. So let me follow that. The 2 kilogram sleeve on A slides on this bar, on the smooth bar again. So no friction between the sleeve and the bar, between the smooth bar. And the mass of the bar is negligible. You can ignore the mass of the bar. Assume that the slider is so heavy that the mass of the bar doesn't really change the whole story that much. And the mass of the bar is negligible compared to mass of the sleeve, let's say, right? To the mass of the sleeve. We are given the stiffness of the spring. I'll just put it here. K is equal to 40 Newton per meter. We are told that the spring is stretched, let's put it this way, is unstretched when R is equal to 0. When R is equal to 0. All right. Supposed to be at t equals 0. The radial position of the sleeve, the radial position of the sleeve is R equal to 0.2 meter. And the angular velocity of the bar, angular velocity of the bar is omega naught is equal to 6 rad per second. Okay, after all this, what we're looking for? We are looking for the angular velocity of the bar, so find the angular velocity of the bar when R is equal to 0.25. All right, a lot of stuff going on there. But the story is still the same, right? It's in horizontal plane, remember that. This is rotating with omega naught. We are given omega naught, angular velocity at position 1. At this position, let's just say not to refer to position 1. 6 radian per second. Now, a couple of extra information. We have the mass of this is 2 kilograms. So I'll put it on here. So you know what the story is. 2 kilograms, right? When the spring is on a stretch, when R is equal to 0, so this spring is on a stretch when this sleeve is all the way down close to the pin when R is 0. Now, when this is going with the velocity of 6 radian per second, R is 0.2 meters. As we said, the sleeve starts moving towards the end of this bar. So R becomes 0.2 meters. What we are asked to find, no friction anywhere. Like a pin is frictionless. There is no friction between the sleeve and the bar. Now the question is, how can we find the velocity of the bar when R is 0.25 meters? Now, put all this long problem statement aside. What we have here is pretty much this. Right? We have this slider, and the only force applied to it is the force of the spring, because the spring is compressed. Remember, spring is always trying to go back to its natural or unstretched position. If it's stretched, it wants to compress. If it's compressed, it wants to stretch. So accordingly, it applies the force in that direction. That would be your force, F spring. And that F spring is K times how much the spring is stretched or compressed. So look at this. We have a force. If this is our coordinate system, think about this as X and Y. We have a force, or the resultant force. There is no other force. This is a horizontal plane, so we don't care about, at this point, gravity and normal force. In this way, at least, we are looking at this from the top, or maybe bottom. Since there is no friction, we know N is equal to mg, but it doesn't really come into play. So there is no friction that we care about. So we have a force which is always, during the motion, is always towards a fixed point on or reference frame, fixed reference frame. Fs is always towards the origin. That means we have a central force motion. Since we have a central force motion, instead of this big equation, we'll just go into this one. And the whole idea of angular momentum is constant during the motion. So let's start from there. Central force motion, let's say we have a central force motion. Right? So angular momentum is constant, right, during the motion, which means we are talking about two positions. Position 1 is when R is 0.2, position 2 when R is 0.25. All right. So HO at 0.2 is equal to HO at 0.1. Well, let's just write it in general. R1 cross M V1 is equal to R2 cross M V2. Oh, M, we don't care, right? Since they're on both sides, we can just get rid of M. So basically, let's write it now in more formal way. These are vectors. I should remember to put always vector sign there. So R1 is 0.2, right? Which means it's 0.2 ER cross R. This is your, let me put it here, make sure that everyone follows. This is X and Y. This is X, this is Y, this is R. And as a result, you have, you can do a little better, you have ER, E theta. Right? You have ER, E theta. Well, R1 is 0.2 ER. Here. 0.2 ER is equal to, multiplied by or cross V1. Now, V1, let me write it this way. V1 as vector and write it here. V1, we have VR ER plus V theta E theta, right? VR ER. This means this is R dot ER plus R omega E theta. Now, R dot, where are we? I lost the train of my thought. Moving things around. Or, okay, I said that. Then we are replacing this. Okay. So this one is R at this position. I have to be more R1, R1, omega 1. Now, R at this position is 0.2. Omega is 6. There is no R dot, right? It was just basically, we are looking at the specific position, nothing is moving in R direction. All right, just we can get rid of this 0. So this becomes, V1 becomes R1 omega 1 E theta. I'll plug it back here. I'll put it back later. This is R1 omega 1 E theta. Maybe it would have been better if I just write it directly instead of making it crowded here. So this becomes R1 omega 1 E theta. R1 is 0.2, omega 1 is 6 E theta. On the other side, I have R2, right? If I can find it. R2, which is 0.25 ER cross V2. Now V2, the kind of same story that let me write it here. V2 is something that we are looking for. V2, let me make sure that I'm doing the notations right here. I told you R1, V1, and then let me not do it. Sorry, guys. Let me just do it in a better way. I think this is what I'm doing here actually is making it difficult to follow. You tell me. Let me do it this way. Let's do it this way. Let's say V2 is something I'm looking for, velocity at 0.2, and say I have no idea what that is. All right, so let's put R1 cross V1 divided by R2. All right. Now R1 is 0.2, right? So it goes 0.2 ER, because I was getting ahead of myself, giving you something that it's easier to just mathematically look at it. V1 is R dot ER, right? R dot ER plus R omega E theta divided by R2 ER. Now looking at this, do the math there. This multiply cross this one. I have to have a cross here. and this cross this one, that becomes, well, ER cross ER, right? That's, I made that term 0 without explaining. So this is better. ER cross ER becomes 0. So the first term is gone, right? Now the second term, you get 0.2 R omega EZ divided by R2 0.25 ER. See, that makes more sense to you. I hope it does. Two cross products, ER cross ER will become 0, ER cross E theta becomes EZ, right? And I have 0.25 ER over there. And these are the values I have. R is R1. We're talking about R1. We should put it here. Omega 1 is 0.2, omega is 6. So that'll give me V2 is equal to 0.2 times 0.2 times 6 EZ divided by 0.25 ER. Right? You do that, that'll give you 0.96 E theta. I think so. Let me double check. Yeah. Now, once you get your V2 as a vector, right? We are trying to find the angular velocity of the world. I hope this procedure made more sense than what I was doing before. So once you get V2, you can find omega 2, right? Angular velocity at point. Once you know velocity, this is V. So omega 2, well, V2 since, let's put it this way, since V2 is R omega 2, right? That we already know. As a result, omega 2 becomes, this is R2 divided by R2. V2 is 0.96 divided by 0.25, whatever that value becomes. I think you will get probably, hopefully, 3.84 rad per second. I made this example more complicated than it should. I'll give you a few moments to see what we did there if you're taking notes. So let me just do a wrap up. Hopefully that gets better. So we have this central force motion. We established that. Now we said since we have a central force motion, angular momentum stays constant at any 2 points, at any given point, so between 2 points during this motion. So I just basically wrote that. I said R1 cross MV1 is equal to R2 cross MV2. Now, position 1 is the position at which R is equals to 0.2, and we know the angular velocity at that position is 6 radian per second. Position 2 is the position that R is 0.25 meters, and we're looking for angular velocity in that position. Right? So we don't have any information about the velocity at point. So I said V2, will move things around. R1 cross M1, R1 cross V1 is equal to R2 cross V2, got rid of M, R1 cross V1 divided by R2. So I should have, no, it's good. So I did the cross product. I put V1 as R dot ER plus R1 omega 1 E theta. Right? It's in polar coordinates. I said when you see central force motion, go for polar coordinates. R1 cross ER first two, the cross product of the first two becomes 0 because ER and ER are the same. Then ER and E theta, cross product of these two becomes easy, right? We had this ER, E theta, E Z. So cross product, just follow the arrow. ER cross E theta gives you E Z. I had the position at point 1, I had the angular velocity at point 1, and I knew the position at point 2. So I got velocity. I got my velocity is 0.96. Now, once I know velocity at point 2, well, velocity polar coordinate in theta direction is equal to r omega, right? So I can find angular velocity at point. I did twist this problem too much, so hopefully it makes sense to you guys. Just gonna wait a little bit. All right. Question on this one, guys. So we did use the special case, right? The case in which we have central force motion, so angular momentum is equal at any given is constant during the motion, so it should be equal at any 2 points. I have another example for that case. Well, when we have central force motion, I'll give you the problem statement, then we'll solve it in the next class, because it includes both central force motion and I added, I specifically brought that example because then you are going to use also linear impulse. So we're going to use both and see how we can actually use both to solve the problem, as if things were not mixed up already. And then we'll do an example that basically includes friction. So you can't get rid of the left side and you have to use the general force. Let's put that example, then I'll come back to this in the next class because it needs explanation. Now we have, let me see if I can find, this is the reason I brought this, there you go. So here is the general story. Right. We have a disk, a small disk, sitting on a smooth horizontal, let's say, surface or table. We give it some initial velocity. We give it a notch kind of in this direction. Push it, it starts turning around. And now we want to actually study this motion. That's the general, at least, setup of the system. So there's this small disk sitting on this big table attached with a rope or a wire through a hole in the middle of this table to some hook at the bottom. We give it some velocity, some push, it rotates around, starts rotating around. Remember, no friction also. It's a smooth surface, so it keeps going. This is also horizontal table, right? We're talking about a table like this. This is more obvious, it's horizontal, there's no top view. Now the problem statement is this. Then we'll come back to this in next class. A 2 kilogram disk slides on a smooth surface well, smooth, that's right, smooth horizontal table, and is connected to an elastic, you don't need to worry about the term elastic at this point, elastic cord whose tension is T is equal to 6R. So the amount of force in this cable, like this cord, is, it depends on the position R. The farther you get is elastic. So I lied about, you don't need to worry about the whole elastic story, meaning that it can stretch A little bit, to some degree, depending on how elastic is that. You can think about the rubber, right? Meaning that R changes, right? It's not a typical kind of chord that we have. That's what they're trying to say. So depending on how far you are, the force in this chord changes, right? The tension force in this chord changes. So that force is a function of R. 6R Newton. Where, let's add this, where R is the radial position of the disk in meters. All right. Now, it says if the disk is at R equals to 1 meter, right, some moment, and is given an initial velocity and initial velocity of 4 meters per second in the transverse direction, what are the magnitudes, or the magnitudes of the radial and transverse components of its velocity when R is equal to 2 meters. All right. So transverse, they mean, by transverse, they're trying to say theta direction. So this is R direction, this is theta direction. That's what they mean by transverse, right? In this direction. So we give it when the disk is sitting at 1 meter away from this hole, right? We give it some velocity in this direction, some initial push, right? Some initial velocity, 4 meters per second. And what we want to find out is that we want to find out the magnitude, or basically we want to find out the velocity when R is equal to 2. So when it starts rotating around, this chord elongates, goes from 1 meter to 2 meters. That's a very weird chord that elongates a lot. But for the sake of this problem, let's say it goes from 1 meter to 2 meters. Right? And obviously the tension in this changes. So remember, the whole reason that we are using energy methods and momentum methods is that in so many cases we want to get rid of, or we want to ignore what happens in between 2 points. Newton method, we have to follow the object and the rigid body and keep thinking what happens at any given moment. But energy methods generally, and momentum methods also part of those, is that we care about where we are at any given moment. In most cases, as long as we can safely ignore friction, or we're not worried about like non-conservative forces, we don't care about what happens in between, which makes our life much easier. Right? Just here we are at the beginning, here we are at the end. If this is the condition at the beginning, what are the conditions, or what is the condition at the end, or at point 2? Compared to you're ignoring so many, whatever happens in between, you don't care. Right? So that's the beauty of these methods, if you want to think about this. This is the case for this one. We'll talk about this Pretty much this is also a central force motion because T is always towards the center. If you think about your coordinate frame somewhere here, ER and E theta, if you want to think about it this way, ER, E theta attached to this chord. So you're going to have a central force motion again. But we are going to use both principle of angular impulse and momentum and principle of linear impulse and momentum to solve this. I will see what the story is. All right, folks, I'm just going to stop here.